Hello and welcome back. So in the last video, we were talking about false discovery rate and how that is a valid way of doing a post hoc pairwise comparison, um, checking, to see if any of these groups are statistically significantly different after doing an ANOVA. Okay, now I'd like to talk just for a bit. I don't want to talk about this forever because I could, but I'm not. I would like to talk about when to use what, why some of these are quote unquote better than the other ones, and maybe why we got different values for the p-values within these tests and between these tests. Okay, so I've got this slide here. The code that I used to make this table is up here. Don't worry about it. I just put it up there for your own reference. But I've got each test in the column here and each group, each pairwise comparison as the rows. Okay, so we have the Tukey's test, Bonferroni's test, and FDR, okay, in these columns. And then the p-values that go along with that. Okay, excuse me. So in all of the tests, we came to the conclusion that yes, there is a difference between low protein from beef and high protein from beef as far as the weights of these rats go. Always trying to bring it back to the context, right? So there is a statistically significant difference between the weights of rats on these two diets, okay? And every single test concluded that, okay? There was no discrepancy. Excuse me again. Sorry. I've been talking, I feel like, forever. And I'm sure you're thinking the same thing. Anyway, so that's good. It's always kind of a good idea to do a bunch of different tests, in this case, these three, just to make sure that you're making kind of a consistent conclusion, okay? Now, let's kind of look at the rest of the p-values, because this was the only group, this pairwise comparison here, that was significant, statistically significant. All the other groups were not. However, some of these p-values are close to 0.05. They are not 0.05 and still over, but they're close, especially this one right here. Cereal and low protein and beef and high protein. That p-value is almost 0.05 based on the false discovery rate test. Okay. Now, Bonferroni is very strict, right? We saw that as the number of comparisons you make go up, the alpha that you use to compare goes way down, right? And it's doing that math for us, so it automatically adjusts the p-value. But notice this test is very, very strict with the comparisons that you are and aren't making. Okay, so we see that reflected here with these really large p-values, this p-value of 1. Okay, let's remember that p-values go from 0 to 1, right? So you can have nothing over this and nothing less than 0. Okay, you can have really, really tiny values and really large values, but that's kind of the bounds there. Bonferroni is being really strict. It's giving no credit. It is saying that there is not a single difference, even in the slightest bit, when you compare these three, this and this, this and this, this and this, right? Whereas, FDR was a little bit more relaxed. Again, the conclusion is still the same, that there is no difference, but we get a little bit closer to saying that maybe there is a difference, especially when we look at these p-values here, okay? And the same can be said with the Tukey as well for the cereal, low protein, beef, high protein, right? We don't have a p-value of 0.05, but we have something close to it, right? So all of these tests are legitimate, right? They're all totally fine to use. You are free to use whatever. I'm partial to Tukey's because of the output that it gives you, but there are plenty of other people that use Bonferroni and FDR and whatever else. Okay, these are all legitimate ways of doing pairwise comparisons after an ANOVA. But the conclusions you make might be different depending on the test that you use. Okay, so I've got this next kind of table here. And the thing I want you to notice is this first row here. We have this idea of strictness in these kind of comparison tests, okay? Tukey is very much in the middle. It does a really good job of not being too strict, but not being too relaxed either. It does a good job of kind of telling you the truth, at least historically it does. Of course, there's exceptions for everything. But Tukey will usually never tell you, that there is a statistically significant difference when there actually isn't, okay? If we go on to the other end here, FDR is very liberal with its sort of way that it does comparisons. So, excuse me again, sorry. So we may say, if we were to do an FDR test, and we'll kind of go back here, if we were to get a bigger sample, these p-values here, these three, they may all be under 0.05, right? These are always kind of changing if you were to add even one new observation in, okay? These are ever changing. And we might accidentally say that, yes, these two groups are statistically significantly different when really they aren't, right? FDR is very relaxed in those kind of claims, okay? And then on the total other end, we have Bonferroni that is super conservative, okay? Now, we can kind of skip these two things, but the next row I want to talk about, good for when you need, okay? Bonferroni, anytime you do see a statistically significant difference, a p-value under 0.05, you can be damn sure that that is truth, that is reality, that there is a statistically significant difference between these two groups on a population scale, okay? You can be very, very certain that this test is telling you the truth, okay? Whereas FDR is better at making just kind of casual implications, okay? So again, all of these are consistent with the conclusion that these two groups are different, but we are also getting closer to saying, well, maybe we should look a little bit more into these comparisons as well, and then after that, you may do more tests, or you may grab more samples, more observations, and then these p-values could go up and say, okay, actually Bonferroni and Tukey were a little bit more correct, or these may go down. It's totally data dependent, right? Okay, so FDR, very good at just saying, well, maybe let's look into something. Bonferroni is, if something is statistically significant, you are pretty sure that you're not making a mistake in saying that they are different on a population scale. I like Tukey. It's the best. I think it's a good combination of these two. The output that it gives is gorgeous, I think. Not to nerd out or anything, because it gives you all of the information that most people want. Okay, it's also pretty quick too, and it's a pretty good middle ground between strict and not so strict. And we also have a relevant in kind of row here, and we can kind of see that Tukey is becoming more popular, which I think is great. Bonferroni is used in like microbiology when you're comparing like cells, one cell to another cell, or some thing within a cell to other things in another cell. Obviously, there's a lot of cells in general, and also like in any kind of one experiment, you may be dealing with thousands of comparisons. Bonferroni is good in that kind of sense, because you don't want to accidentally say that there is a difference when there isn't really. You want to be sure that any differences you do see is truth. And then FDR, to be totally honest, I'm not totally sure when you would really want to use this. It's very casual, kind of liberal in the conclusions you make. If you don't want to test, so we'll kind of come back here. Let me actually, instead of this, let me just go back here. Let's say that you didn't want to compare every single combination of things. You only wanted to compare just a couple of groups, but you do have the data from these other groups. Maybe FDR is your way, okay? And then, so you may want to just do 3 comparisons at first, maybe these 3. And then you say, okay, FDR did whatever. Let's add another comparison and see how that changes. That's the only kind of time I can imagine that's useful. Again, that this is totally up to you which one you want to use. I like Tukey the best. So as a recap, because we just covered a ton. Oh my God, we just covered a ton of information here. There are the whole classes based on ANOVA. Okay, and we just covered kind of the simplest version. Not to say that it's easy or anything, because it is a lot of work. Okay, but we can kind of follow this workflow with ANOVA and just in general too. So you read in the data, summarize the data based on each group, and we've kind of have that reflected back here. So we summarize the data by group. Of course, we read it in. And then create a box plot for each group. Did that, bingo. And then model, make sure you look at the residuals to make sure that you can actually trust the results. The thing here is that if you're doing ANOVA and your p-value is greater than 0.05 for that model, then you don't need to do anything else because there is no difference between any of the groups. All of the groups are virtually the same. Okay, so if your ANOVA comes out with a positive p-value, or I'll say maybe not a positive p-value, but a positive outcome for the model, p-value is less than alpha, then you analyze the residuals and then do any one of your post-hoc tests to look at the differences between the groups. And then after that, you report your results. Now, what do you report? Okay, so these are kind of the three things that you want to do, and then after that you make a bunch of money. So the first thing you want to report is the p-value from the ANOVA, and I have an example here. This is a study that I worked on a really long time ago, but I report, let's see, the p-value. Sometimes the f-value is also given. So this is still the the distance your data is away from 0 in standard error units. It's a little different because we have more than 2 comparisons. And so that's just something to kind of tell you the overall intensity, we'll say, of the differences in your data. And that looks something like this, right? So you can ignore this FWIC and BMI, whatever. But we have an F value that I give and then a P value for the ANOVA, okay, for the ANOVA. And then after that, you report which pairwise comparison test you used, and then what groups were statistically significantly different. Okay, so that's kind of the general idea here. And you don't have to so much focus on this. This is just an example. But I give the F value for the ANOVA, the P value from the ANOVA, the test I did, Tukey's honest significant test, and then the P value associated with that. Okay. Very cool. I think this is really awesome. This is a really strong test. ANOVA is used all the time. It's frequently used. It is very, very strong. It is very robust. You can do a lot with it. Okay. Oh boy. So with that, that's ANOVA, and that's post-hoc comparisons. We're going to be moving on to regression next. Now, if I've timed this correctly, I think it's spring break next week. I think. So we'll kind of come back after that with some new topics. They're related, but we'll be switching up the format of the class just a little bit too, which is cool, I think. Keep you on your toes in a good way, right? We're not here for monotony. Okay, well, with all of that, good work on this. Thanks for watching all the way through. If you didn't, I'm sorry. For you, not for me. And I will see you in the next one.